Colpitts oscillator is very similar to Hartley. So Colpitts is very similar to the Hartley oscillator. The only difference is the tank circuit design. So in Hartley, what we have done the tank circuit design by using two inductors in series or the taped inductor and one variable capacitor or the capacitor in parallel. So this is the tank circuit of Hartley oscillator. In Colpitts oscillator, it's totally the opposite. So here you can see this is the tank circuit of Colpitts, and we have only one inductor and we have two capacitors in series. So they are in parallel combination. So then we can call this as a Colpitts oscillator. So these are the people, the scientists who invented these oscillators. Colpitts and Hartley, these are the name of somebody who invented this. That's why we call this as a Colpitts oscillator and Hartley oscillator. So everything else is the same. So here we have the tank circuit in the feedback, and we have the transistor as the amplifier, and we have the biasing resistors, and we have this coupling capacitor and blocking capacitor, and everything here we have this radio frequency choke in the collector. Everything else is same as this circuit almost. Okay, so Colpitts oscillator design uses two series capacitors with center taped and a parallel inductor to form its resonance tank circuit. So this is the tank circuit. It generates sinusoidal oscillations. Okay, so the Colpitts oscillator uses a capacitive load, capacitive voltage divider. This is the voltage divider as its feedback source. The two capacitors C1 and C2, these in the tank circuit, C1 and C2 are placed across a single common inductor L. Then C1, C2 and L form the tuned tank circuit or self-tuned tank circuit with the condition for oscillations being XC1 plus XC2 is equal to XL. So what is this XC1, XC2? That is the capacitive reactance. Capacitive reactance of the capacitor 1, capacitive reactance of the capacitor 2 is equal to the inductive reactance of the inductor. The same as for the Hartley oscillator circuit. Okay, so then the advantage of this circuit is it has less self and mutual inductance issues within the tank circuit. So here you can see the mutual inductance. So if you talk about the Hartley oscillator, there is a mutual inductance. So that is not really wanted one. So we do not have the same problem here in Colpitts because here we are using just a single inductor. So the frequency stability of the oscillator is improved along with a more simple design. So you can see here the circuit design is little more simpler than the previous one. In the previous one, you can see here even in the emitter we have this R and C parallel combination, and we have this kind of center taped inductors L1 and L2. But here the circuit design is little more simpler. As with the Hartley oscillator, the Colpitts oscillator uses a single stage bipolar transistor amplifier as the gain element. So that is for amplification purpose, which produces a sinusoidal output. So operation is same as Hartley. So this one you can, whatever we discussed here, the same here. So we are applying the base voltage. Based on the base voltage, this collector current will vary because we can make it either open circuit or short circuit of these transistor terminals, collector and emitter. So based on the short circuit or open circuit, the voltage current level or the voltage level will be different at this collector. So here we are taking the output, and here we have the DC components blocking capacitor or the coupling capacitor. We can also call this as a coupling capacitor. So in any this kind of transistor design, you will learn about voltage divider and blocking capacitor, bypass capacitor, coupling capacitor, and so on. But the, the function of all these capacitors are the same. Either the capacitor will block AC components and allow only DC component, or this is the case 1, and the case 2, it will block DC component and allow only AC component. It will be acting like a filter. So here we are using this case, second case. So this capacitor will block the DC components and then it will pass only the AC component. Okay. So now we will see the oscillation formula. So the frequency of oscillations for a Colpitts oscillator is, this is the formula. So it's really based on the tank circuit design. So FR is equal to resonant frequency of Colpitts oscillator is equal to 1 divided by 2 pi square root of LC. Here L is just only single inductor, so no problem. But the capacitor is based on two values, right? C1 and C2. So C1 and C2, they are connected in series. So the effective capacitance value is equal to CT is equal to C1, C2 divided by C1 plus C2. So how I I got this formula? This is the standard formula for the whenever we connect the capacitor in series. So 1 divided by C1 plus 1 divided by C2. So that is the effective capacitance reciprocal. So if you just modify this equation mathematically, then you will get this is the effective capacitance so of C1 and C2. So this is so it's a little bit different between the resistor and inductor and capacitor. So you should know this difference. You are an electronic or electrical engineering student, so you should know this. So this is R1, R2, and this is L1, L2, and this is C1, C2. So here R1 and R2 connected in series, right? So the effective resistor value is what? R is equal to R1 plus R2. Very simple. And here we have the two inductors. So the effective inductance value is L is equal to L1 plus L2. So here, but the capacitor is totally different. So C1 and C2, the effective capacitance value is C is equal to C1, C2 divided by C1 plus C2. But similarly, if you make the parallel combination, then what will happen? Resistor. So I have R1, this is R1 and this is R2, let us say. Now these two resistors are connected in parallel. So it means these two terminals are connected together, these two terminals are connected together. Either you can apply the VDD and then the ground. So it's not a matter, but it's in parallel. So what is the effective resistor value? R is equal to the same 1 divided by R1 plus 1 divided by R2. So here same like this capacitor. So here we have to write R1, R2 divided by R1 plus R2. So anyway, so these are some kind of the standard things. You should know how to calculate the equivalent resistor value when it's in series connection or when it's in parallel connection. Similarly, the capacitor, this is for the series formula, right? But for the parallel formula, what is the parallel formula? So the capacitor is opposite of the resistor. So here two capacitors are connected in parallel. So C1 and C2. So what is the effective capacitance value? C is equal to C1 plus C2. So it's opposite. So resistor is parallel means we have to use this formula, capacitor, this formula, but in series it's the opposite. So just anyway, so here is you have to remember the resonant frequency formula 1 divided by 2 pi square root of LC. C value is equal to C1 C2 divided by C1 plus C2 because these capacitors are connected in parallel. So you try to make something by yourself on the paper or whatever. You can make the series combination, and you can make the parallel combination of each. So here we did not mention about the inductor. So, and then you can write the formula. So you can apply some value. Maybe you can apply like 1 kilo ohm, 1 kilo ohm. So effective will be just like a 2 kilo ohm very easily in series resistance. Resistors are connected in series. So resistors are connected in parallel. So I apply the same 1 kilo ohm and 1 kilo ohm, 1 kilo ohm, 1 kilo ohm. So then the formula is totally different, right? So here, what is that? 1 multiplied by 1 divided by 1 plus 1. So this is equal to 1 divided by 2. So it is 0.5. I don't know, you can see that. So 1 divided by 2, the effective resistance value. And then this is going to be 0.5 kilo ohm. So you can see the resistor value got decreased because of the parallel combination, because the current is flowing this path and also current is flowing through this path. In series means the current is flowing through only one path. So it means these two resistors are giving opposition to the current flow. So you are adding the resistance values. So this one is trying to block some current, and this also trying to block some current. So we are adding this in this fashion. But if you connect in parallel manner, so the current is having two direction, two path. So one current will flow I1 here, and then one current will flow I2. So the resistor value got reduced as a half. That is why it's like this. This is some kind of a numerical analysis. You can make some formulas and then you can analyze this by yourself. These things, I think you should study these things already in your circuit theory course, I think. So this is the formula for Colpitts oscillator, frequency of Colpitts oscillator, frequency of oscillations in Colpitts oscillator. So I think we are done with oscillators. So far, we had seen the basic theory behind oscillators and different types of oscillators.